Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. My guest today is Professor Ghassan AlRegib, who is professor in the School of Electrical and Computer Engineering at the Georgia Institute of Technology. He is also the director of the OLIVES Omni Lab for Intelligent Visual Engineering and Science, as well as the Center for Energy and Geoprocessing. Welcome, Ghassan.
Thank you, Gill, and thank you for hosting me.
Yeah, thanks for doing this. So we have a number of very interesting areas to talk about in the area of artificial intelligence, deep learning, neural networks. And I want to start with one of your papers, Backpropagated Gradient Representations for Anomaly Detection. You say in this paper, learning representations that clearly distinguish between normal and abnormal data is key to the success of anomaly detection. Most of existing anomaly detection algorithms, you say, use activation representations from forward propagation while not exploiting gradients from backpropagation to characterize data. Now, just to set the context, Ghassan, neural networks, perhaps 60s technology, deep neural networks, cheaper silicon, and improving mathematical techniques have brought it to a level that is becoming interesting and more interesting every day.
Absolutely.
But obviously, there's some mathematical challenges. When we look at the brain, it is able to learn things with very little data. It's really, really good in detecting anomalies, whereas deep neural networks requires typically a lot of data for training. They don't necessarily generalize that well, and then anomaly detection is a more complex problem, right?
Absolutely.
So this idea that you can use the gradients in the backpropagation, backpropagation way, you can use gradients to detect anomaly. Could you describe a little bit about how you do that?
Yes, absolutely. And I think you kind of gave really very nice kind of foundation to this work. And if I may add I'm going to go a step backward a little bit from anomaly detection and gradients, and look at the neural networks in general. What happens, as you describe, there is a training phase where you have a certain data, and you have this deep network. There's a bunch of neural networks with different hidden layers. And in short, basically, there are certain parameters, we call them weights and biases within this network. And the whole idea is that when you feed these images or this data, images as an example in this case, and then you keep propagating all the way with some kind of initial weights, And then at the end, basically, you have this kind of whatever your application is, classification or segmentation or recognition and so on. You kind of have the ground truth for your training data, and now you kind of start to compare how good your feed this network basically produced the predictions compared to the real ground truth. Yeah. And then now you have an error, and then you start to backpropagate. And in the backpropagation mechanism, you do quite a bit of optimization to really come up with the right, a good weight value. Basically, that's what the whole training is, to find these parameters, these weights, these activations.
Yeah.
And in doing so, you are really doing optimization, meaning they are really relying on a gradient, and you are really kind of trying to compute these gradients that will generate for you kind of the optimal or the trained values for your weights or parameters in the network. And one of the most challenging application is, as you mentioned, is we train the networks on a specific type of data, and then this generalization concept, how we can generalize this knowledge to cover other data that's not really part of the training. Yeah. And the challenge, and usually in deep network, is it doesn't really know when it doesn't know, right? The challenge is that it always have this kind of built-in enforcement to make a decision, right? But not all decisions are correct, because it may not even fit the model itself. So that's basically where actually a big part of our study started 4 or 5 years ago, is to look into ways how we can empower the network for a couple of things. The first thing is we would like to equip the network, the neural network, to know when it doesn't know, which is, I think, is very, very important. And the second one is we would like it to kind of differentiate between its knowledge space or subspace and compare that with what data that's really outside that learned space. And that's where anomaly detection comes into play. And as you mentioned, the applications are really tremendous, but the challenge is if I train, as an example, and this is very, very famous kind of simple data set, we call it the MNIST, where basically you have handwritten digits. There are 10 of them between 0 to 9. And then if you train on really 0 to 8, for example, right? And then now you enter, so you have a training model, you finish the training, you have your model ready, and now you input and you're testing the digit 9, an image of the handwritten digit 9. Yeah. And now it hasn't seen it, right? It hasn't seen 9 in the training. And now the question is, how will this network detect and recognize what digit it is? And what the previous works have been, and so the challenge in here is for the network to say, I haven't seen this. This is an anomaly compared to the other digits. So this is a very known problem. And what people have been focusing on for quite some time on really using these activations, these weights, as basically the main feature characterizing a model or a deep network. Right. So what we started to look at years back to say, what about the gradients? How the optimization algorithm go from one step to the next? Where we're doing this gradients calculation, the gradients themselves are really the source. Actually, if you look at the activation and the weights, they are nothing but the output from the gradients. So we said, ask ourselves, these gradients have really quite a bit of information about two things. One is the model itself, the neural network architecture itself, as well as the data. Right? So that's when we start exploring how that gradient information captures the data and decide if it's anomaly or not.
So for my own understanding, Ghassan, let's say it's a supervised classification problem. We have a bunch of pictures of dogs and a bunch of pictures of cats, and we train a deep neural network, it learns how to differentiate between dogs and cats, and if you show it a ship, it will potentially put that into a dog or a cat category, right? Because that's all it
Yes,
knows.
exactly.
But the brain is so good at this that the brain will immediately know it is, I just don't know it, right?
Exactly. Yes.
And so it's a complex mathematical problem, the anomaly detection. And so if I understand this correctly, Ghassan, so in a typical training process, we have the weights, we have the forward propagation of the weights, and then the back propagation of the gradients is almost like a necessary evil, right? We don't necessarily use that in the process, right? It's just sort of trying to figure out how to redistribute the errors. Is that what happens?
Yeah, so exactly. So the gradients come into play in the training, and then after you finish the training,
Yeah.
all what you have is basically the weights and the activations.
Yeah.
However, during that training piece, even after actually in the inference, even when you really input this picture of a ship to your already trained model, right?
Yeah.
At the end, that model will produce a decision, as you mentioned, like a cat or a dog, that's all what it knows. Right. But now, what we said, let us really backpropagate that thing at the end, that there is a vector at the end that maps to dog and cats and so on. Let's really backpropagate that and see basically how much, and that's actually where in that paper we described in some figure, we can just kind of a visualization, an illustration, to say that's like figure, the second figure, where we have, you can imagine there is this kind of a hyperplane that's really where the dog and the cats exist, but the ship is such a data that's very far from this hyperplane. When you backpropagate, what we found out, basically, those calculation of the gradients tell you basically that this point of the ship is really far from the hyperplane. Not only that, basically it has more than that, like how far and in what direction. So is it really in line with the hyperplane, or is it perpendicular to it, or so there is also a direction. So there's quite a bit of information in the gradient when you backpropagate in the inference, which we never do in typical networks.
Yeah, it's fascinating. So again, if I understand this correctly, Ghassan, so in the backpropagation process, because the network essentially has to come up with a binary answer, it will ultimately put that into cats or dogs. But what you're saying is that during the backpropagation of the gradient phase, there is information there that if you study that would tell you it is anomalous?
Exactly. So what you backpropagate, you say, assume that the network decided that this is a dog, right? And then you say, okay, let me backpropagate that information.
Yeah.
And now what you find when you backpropagate, that the gradients will be changed quite a bit because this input image, it's not something that the network saw during training. So now it has to associate this label of a dog with this kind of an image, which is totally new. So now the gradients have to work much harder. So you have, the network has to work much harder to have, and the gradient will have larger values, maybe more direction, more entry, more information in them. So the network has to change quite a bit to add or accommodate for this anomaly data.
Yeah. Is it mathematically possible, Ghassan? So suppose I train a network rather than just a binary classification, but I have a third bucket. And the third bucket is noisy data. I'm just making this up. I have cars and ships and airplanes and so on. And so is there a mathematical way to say, if I can't figure it out, if it is not a dog or a cat, then I'd put that into a third bucket? Is it possible to train it that way?
Yeah, that's a very good question. And so there are these attempts, and these are kind of established, to have this kind of what we call the other, null space.
Yeah.
So anything that the network cannot, with a certain level of certainty, decide this belongs to class 1 or class 2, then let me put this into the null space. And the null space, you can think of it as the other. Basically, everything that I cannot really see into this, into the two classes. And the example you mentioned that with the noisy data, that basically is really a very good example, because that's where we test robustness of models for such a noisy data.
You have a number of papers in this area that came out recently. One of them is Implicit Saliency in Deep Neural Networks. You say that we show that existing recognition and localization deep architectures that have not been exposed to eye tracking data or any saliency data sets are capable of predicting the human visual saliency. So what do you mean by saliency here?
Yes, so saliency is a feature in the human vision system. And usually, so the idea from computational neuroscience is when we humans look at a certain scene, it's very complicated, very complex scene. There are certain parts in the scene that we really focus on in the first micro milliseconds. And that's basically the most salient part of the scene we're looking at. And that's being really heavily utilized, like in covers of magazines and in movies and in such outlets, because the human basically, we are tuned to look at these salient parts of the image or the video. So saliency can be a spatial. So you can think of, if I have a whole image, just a blue background, and there is an orange leaf there, then definitely the only thing we will look at is just that orange leaf, because it's very different from the surrounding. So this we call the center surround model in a human vision system. And similarly in the temporal, so in the motion, when there is a motion, when we are very sensitive to certain saliency in the temporal axis as well. So the idea is in a human vision system is very, very efficient in not necessarily processing the entire scene, but really focusing on specific part of the scene with the kind of a zoom in focus into that details in that part of the scene. And we use that quite a bit without us knowing as a human and our brains. And now the question we asked ourselves, is there such a thing in the neural network? Is the neural network trying to zoom in into certain part of the saliency? And at which level in the network, at which depth into the network? So this was kind of a study to say, is there such a thing or not? We know that from neural networks, the first layer or two, they mimic like V1 and V2 in the human vision vortex. We look at edges, we look at lines, but we know this. But as you go deeper into the neural network, then we are looking at more context. So this paper was more about, let's really look at the neural network and look in this kind of an application. Is there some saliency mechanism already built in? And it was. I mean, there was the neural network has this kind of an implicit saliency detection by nature of the training part that looks at really what the most informative part of the image to the application and the neural network.
Yeah, it's really fascinating. One of the constraints for the brain is, the energy and the capacity and the bandwidth, so to speak. And so the brain is extremely good in discarding data and really focus on the most important things.
Exactly.
So I wondered, one direction in computer science, it appears, Ghassan, I don't know a lot about it. It appears that because our hardware costs are going down, because memory costs are going down, the tendency appears to be more data and more complex and deep networks. Will that take us away from these types of ideas that perhaps there are more efficient ways to learn things?
Yeah, this is really very brilliant question, and it's a very important question at the same time. And so maybe I can talk about that from my background perspective. I am I'm coming from the background of like digital signal processing and image processing and electrical engineering and applied math. And the idea basically is that, and this is something I discuss actually with my own PhD students almost on a regular basis. And if you look at our work in the last 7-8 years, especially when it comes to machine learning, is to answer questions that will relieve us from just relying on deeper networks and more data. Because at the end of the day, we have to really have a good understanding of what these deep networks are doing. And if only, and this is something actually I tell my PhD students, I really don't care much about the performance if it improves classification by 0.1% in accuracy or so. What I really care about more, do I understand what this network has done to the data and how it reacts to this data? And I think that's really a most, at least to me, is the more interesting problem. It will take us into, it will really produce some kind of paradigm shift, because it will relieve us from having deeper network and just rely on more data. Because if you take the example of autonomous vehicles, for example, or even medical images, there is not enough time and imaging techniques out there to collect all the different combinations and scenarios that could happen, right? So at the end of the day, there will be situations where you don't have enough data to train on. But if you have a good understanding of the insights, like really what's happening in the neural networks, I think that's really the more important and more interesting question. Back to what the point you raised in the question. That's more interesting and bring us really closer to understanding what's really happening around us and even our own brain.
Yeah, you have another fascinating paper in this area, Ghassan. So, contrastive explanations in neural networks. You say visual explanations are logical arguments based on visual features that justify the predictions made by neural networks. And so this is in that direction, right? Predictions are one thing, but understanding why is quite another. And but I think what you are arguing is that the why is quite important than just the prediction.
Yes, and actually, we have worked extensively the past, I would say, 1 year, 1.5 years on this concept. And actually, I'm really pleased that we reached really very interesting revelation about the neural network. And it goes back, actually, if you go back to really publications from the 50s and the 60s in the social sciences and psychology. And the question is usually, so if you look at neural network, there are some quite a bit of papers. They're asked why P, why this kind of bird, for example.
Right.
What we learned from those earlier papers is that there is something very important to ask the question with the following format: why P, not Q? So you bring this contrastivity into the question. And what we found, if we take that kind of model from social science and psychology into a neural network domain, it doesn't matter what neural network you have. You can have the deepest network, you can have the most powerful one or the simplest one. We did extensive experiment in the past several months. And every time when you bring that question of why P, not Q, it empowered the network quite a bit. It becomes much more generalizable. It knows much more and more robust to it. And I'm not talking by 1 or 2%. There is quite a bit of margin in the performance because of this simple question of why P, not Q. And of course, we have to be careful how to do the experiments for the P and the Q. But at the end of the day, the question really what matters is why P, not Q.
So let me see if I understood it, Ghassan. So are you saying this idea that why P rather than Q, that concept can be used to train the network?
Yes. So what happens in here is again, we are looking at characterizing the network, right? So what is in either we are looking at the activations or the gradients. We are still looking at the gradients in this scenario even. But in either way, even if you look at the activations, is the same improvement happens. So what happens is you say, I want to train my network basically to really, I give it a picture of a photo of a convertible vehicle, right? And then ask the question, why did the network classify this as a sports car, right?
Yeah.
And then it will give you basically some kind of regions in the image where it decided on doing that, that classification.
Right.
Now, when you ask the question of why sport, not a sedan, right?
Yeah.
Then what the network basically highlighted is that top part of the vehicle. That was the decision it made to do that. And we applied that to birds, to traffic signs, I mean, a number of different basically applications. And every time there is kind of a unique contrastive explanation. And how we get that basically is really is not necessarily in the training. Or what we want is after the training. So the network is ready, is done.
Yeah.
We have the parameter, but now we want to empower the network basically to have it more refined. So actually, I look at this as really a plug-in. It can be plugged in the training, but also in the inference part after the training. And in both cases, the network becomes more lean, I would say, to really zoom in on making better choices and decisions based on the differences in the images.
Right. And so a network trained in the usual way, you're saying it could be improved by this type of a process?
Exactly. And basically the network could become, so in the training, for example, instead of just coming up with these features and weights using only, like the typical training, you can really add to it when you backpropagate. You say, let me now input, let's say, a spoonbill, as I have in that paper, and then the backpropagate to see what flamingo. So now, how much, back to the question about the gradient, how much the network has to change itself, right, to really figure out the relationship between the two. So that's one part.
Yeah.
But even if you get a ready trained network, now you want basically to understand how the network make decision.
Right.
So you can think of this, and this is something actually another kind of spillover effect of this. I can imagine using this kind of technology to evaluate networks. You can imagine down the road we'll have autonomous vehicles, and each one has different, AI mechanism for, a scene understanding. But you want to test basically if this network really is reliable in a way and in what it does. And I can imagine it is a trained network. It's really done. So can we use this kind of technology to really test the limits of this network? Does it really know the difference between a spoonbill and a flamingo by looking at why P not Q, for example, or why spoonbill not rather than flamingo? And we find that there are tons of other applications that we can imagine that will come out of this work because it brings this contrastivity to the network, which I think is very, very important even for us as a human being. When we look at things through our eyes, we contrast things, we compare things without us feeling that.
Yeah. So sort of a generalization score that you can attach to a trained model, right?
Absolutely, exactly.
But I wondered, so for example, intuitively, I feel like if the heuristics that we find in that process, if those heuristics are simple and easily understood, maybe my intuition is wrong. My intuition is that it will be less generalizable. Is that true or not?
So the idea in here is when for example the network has been trained on really a spoonbill, for example, right? And then it hasn't seen the flamingo before, right?
Yeah.
So now when I make it see the flamingo, I want the network to really tell me which part of the bird makes it look like a spoonbill, which part it doesn't look like a spoonbill, right?
Yeah.
I want to know that. So the contrastive part, it will highlight the differences, which is kind of the neck area, like the S shape in the neck is kind of the most salient part, the difference between the two. But the pink kind of feather and body, they are really very common. So I want to know, and actually this is the extension that I mentioned, the work that we have done.
Yeah.
We kind of split the scene into different aspects. There are aspects that really there is a causality to it, like there is a causal mechanism that because of this, I can decide on this. Like because of the feather, then it will be a spoonbill, for example. But at the same time, there are certain parts in the image that will empower the network to say, because of this part, then it will not be spoonbill, it will be flamingo, right? And I want to empower the network to really see these differences and question itself, and not just to take whatever the training is providing.
I want to touch on one other paper, Ghassan. So perceptual image quality assessment through spectral analysis of error representations. You say we analyze the statistics of error signals to assess the perceived quality of images. And specifically, we focus on the magnitude spectrum of error images obtained from the difference of reference and distorted images. So what's the application here?
Okay, so this is actually, it's under, we spent quite a bit of time working on a very fascinating problem, which is how can we mathematically come up with a measure of the quality of images and videos?
Yeah.
And it's a very fascinating field because it touches on computer science, signal processing, as well as computational neuroscience, as well as color. So it has quite a bit of really quite a broad coverage. So we spent quite a bit of time for many years actually looking at images, videos, 3D visual data as well to assign quality to it. And actually, this kind of work it happened actually as by accident, and we were working on a project about the distortions, like when you train a network to detect a traffic sign, for example, but now you have deployed the vehicle into the real world, and then you have snow, you have haze, you have rain. So we came up with this kind of data sets that have a control. So the scene is the same, everything is the same, but we add distortion sometimes, like a dirty lens or glare, for example.
Yeah.
And sometimes we add environmental condition, like so we did everything in CGI, like rain or snow and so on. And then when we were analyzing to really come up with understanding how the network reacts, part of the work tried to figure out the difference between the distorted data and the perfect or distortion-free data. And then one of at the time a postdoc in my group, he realized when he looked at the distortion part of these images, he found basically kind of a very kind of almost like a fingerprint of these distortions based on different factors, different levels, and so on. And that actually said, oh, if that's the case, given our almost like 10 years at the time of working on quality assessment of images, can we apply this to our quality assessment previous work? And we did, and it gave us really kind of an amazing feature space to really look at this fingerprint, which coming from distortion in the images, to really right away come with an objective measure of the quality of these images, without us knowing what the distortion is or what the noise is. All what we have is just a distorted image.
Yeah, I was thinking, Ghassan, is it possible? So you have a spectral, sort of properties of the error. If that is well understood, is it possible to subtract that and really remove the error?
Yeah. So this whole field of image denoising is a very, very like a 40 plus years of work in that domain, and there are thousands of algorithms. And yes, the idea is that if you can really characterize the distortion and estimate it very well, then basically you can really subtract it and remove from the image. Yes, I mean, that's kind of the denoising. But what we wanted to do in here is that in coming up with an objective, like for example, in a real-time scenario, like in a conference call or a streaming of some game, you have this distortion happening in real life, or even an autonomous vehicle. There are some distortions coming. You want to know first. You don't really have enough time to store the data and denoise it. What you want to know right on the, in real time, if this frame or this bunch of frames are distorted or not. So you can really use them for your detection, or use them for your display or not, or ask the denoising algorithm to denoise. So this is the whole point behind objective quality assessment, to really kind of give a score for every frame in terms of between 0 and 1 is good quality or bad quality.
Yeah. We have more to talk about, and so we'll take a quick break. When we come back, we'll talk about your other papers.
Sounds good. Thank you.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.
So we're back, Ghassan. We have been talking about anomaly detection in deep neural networks, image quality assessment, and so on. You have other papers in this area. One of them is fabric surface characterization, assessment of deep learning-based texture representations using a challenging data set. You said tactile sensing or fabric hand plays a critical role in an individual's decision to buy a certain fabric from the range of available fabrics for a desired application. Therefore, textile and clothing manufacturers have long been in search of an objective method for assessing fabric hand, which can then be used to engineer fabrics with a desired characteristic. So this is a complex problem, and it has features coming from, I guess, different sensations, so to speak. So you want to describe a little bit as to how you go about solving a problem like this?
Yes, this was really a very fascinating project where we were approached by a textile manufacturer, and they rely in terms of quality control on these experts who really sample the product line outputs and then make a decision about the quality. And the idea is that if you really have a more of an automated quality measurement, then you can really feed that back into the chemical processes that really contributed to this manufacturing of the textile. So we wanted to have a kind of a setup where the first thing we thought about is really kind of have this a zoomed in camera into the textile, into the fabric, to really have this kind of microscopic view of the textile. And the challenge wasn't really into getting the data and coming up with features. The challenge that really took the time is really the time we spend sitting down with those experts who, as in many other fields actually, could not really write down the rules they follow in making that decision. It just came up with experience over many, many years of doing this kind of task. And between their eyes, the touch of their hand on these fabrics, they come up with kind of a decision about the quality. And it took quite a bit of time. It took months and months and many, many hours of really trying to come up with these rules until we really came up with a set of them as in the paper. But it was an initial attempt to say, can we really rely on the visual features in a way to have a calculation of the human touch sense and how we evaluate that. And we succeeded to some extent, but I think we barely scratched the surface because even the individuals themselves, their scores of the quality changes from one day to another because of temperatures, because of body temperature, because of moods, because different time in the day. So they themselves basically they have quite a bit of variations, and that's why when we trained our networks, the inputs, the ground truth, actually they were far from being a ground truth because they vary quite a bit. So it took us some time to get these to a certain, reasonable, stable ground truth level before we train the network.
Yeah, I mean, it's fascinating. It appears that the touch and vision sensations, how the brain processes those sensations, appear to be very, very closely linked.
Yes.
Probably because Homo sapiens were, kind of stumbling around in the dark.
Yes, exactly. Yeah, I mean, I think this is very fascinating. There are some works there, and in this work, this project, we collaborated with our colleagues in material science engineering who spent like 34 years of his time, his career on textile engineering and understanding textile.
Yeah.
And it was it's very fascinating because it's not simple. It's not only vision, right? When you see a vision of a dog or a cat, you say this is a dog or a cat. But in this case, it's much more complicated because there is a manufacturing process went through it. But at the end of the day, is the human senses will evaluate and give a score. To mimic that into a machine, it has been it was really a very fascinating project.
Yeah. So the objective here was let me ask you. So an expert by touching a piece of clothing and visually taking in the characteristics of that material reaches a decision. Was the objective to replicate that quality decision of an expert?
Yes. So the idea is that if the expert can sample, let us say, like 10 or 15 samples a day,
Yeah.
right? But there are, 10,000 other samples already in that day, right? That we haven't really sampled, that we haven't provided quality for.
Right.
So can we have a kind of a continuous kind of learning, like a learning mechanism that's alive, that keeps learning from that expert with time, and eventually it will mimic what the expert would score such fabrics, and that's basically the idea is to create such a living model and initiate it, and that was exactly what the aim was.
Very successful.
So I have to be careful in saying yes or no there because, as I mentioned, I think in my concluding report to the sponsor, we were very, our recommendation is we need to go through, we had access only to one expert, but they have 5, right?
Yeah.
So this is a long-term kind of process, and you really need to access all the 5 experts because they are different age and they are different gender, and they have different background experiences. At the same time, you want as much as possible data from them to kind of to better understand the relation between visual and touch. Yes, the model actually we created, they took it, and given the agreement, I don't know yet what happened within the company, but I think giving the data and the score they gave us, it was successful for the project. But for me to use this in textile factories, I think there's quite a bit of other work to be done before we rely on it.
Yeah, I mean, it's a fascinating area because the expert, I would imagine, cannot really explain the why. They can probably only say what they like or what they don't like, and so the processes fairly subjective in some ways. We have similar things in business context. People tend to make decisions. They can't really explain why, but some of them seem to be pretty good at making decisions. And so this may have applications in that direction. Can we take an expert's sort of, let's call it subjective process and make it objective in some sense?
Absolutely, absolutely. And this, what you just described, it took quite a bit of time because it took many hours, many meetings over many months to really come down to kind of 6 kind of fabric features.
Yeah.
And in the textile engineering, they have quite a bit of literature about what these features are. However, to map these features to the quality is the challenge. And I saw that in other works that I did with geophysics, with medical doctors even, like when you go to, and you mentioned the business, basically a decision-making process. And the same thing in medicine, right? I mean, you have different diagnoses, different opinion from different doctors, because, and even the same thing in scientists, like a geophysicist, for example, that I worked with very closely. And the challenge is that basically kind of, they come with a decision, and then why it takes a lot of effort to explain why they make that decision, because it's not straightforward to write it down onto paper.
Yeah, it's not straightforward, and it takes a long time for an expert to get that expertise.
Absolutely.
And so this is one of those situations where the brain is, brain is taking in lot of data, lot of cases, and lot of experience-based training for the brain, and ultimately reach that expert level, which is quite different from what the brain typically does. So
exactly.
It's interesting that I think there's a lot of interesting applications for something like this.
I agree, absolutely. We barely scratch the surface of understanding the brain, but this kind of experience, how can you? That's why, I mean, is it more data and time for the neural network? I think it's more complicated than that, and experience is a very interesting extension to all these machine learning networks.
Yeah, sometimes we talk about humans having intuition, which is sort of an experience-based thing. But I think how humans make decisions is also heavily dependent on the initial conditions they were given, where they grew up, what their culture was, and so on, what their education levels are. And so there are things that sort of get intermixed into a decision process that is, at least on the surface, appears subjective.
Absolutely. I mean, that's exactly the background, right? I mean, there is the human is every human is really a complex system, and from the days of basically when that human was a baby, you have all these senses, and they're just basically collecting not data but experiences and adding these, and this can be culture, it can be background, can be family, society, and then technical, it can be learning, and so on. So all of these, they come together, and that's why it's very fascinating to kind of understand the human nature, and see what we can learn from it for machine learning side of things. But at the same time, I always warn my students that I think there's a very common example in the machine learning. You see, when we design airplanes, we didn't really have exactly the mechanisms of a bird, right? But we got inspired by it, right? And that's the whole point of understanding the human, to be inspired to design machine learning networks to do that. But the human is a very amazing, basic kind of machine in that sense, and it's very complicated to understand as well.
Yeah. You have another paper in a different area. So successful leveraging of image processing and machine learning in seismic structural interpretation. You say as a process that identifies geological structures of interest, such as faults, salt domes, or elements of petroleum systems in general. Seismic structural interpretation depends heavily on the domain knowledge and experience of interpreters, as well as visual clues of geologic structures as texture and geometry. With a dramatic increase in the size of seismic data acquired for hydrocarbon exploration, structural interpretation has become more time consuming and labor intensive. I used to be a structural engineer, Ghassan. I lost most of it now. But I sort of understand what you're talking about here. So this is one of those situations, again, where we rely heavily on experts to make a decision based on large amounts of data, right?
Absolutely, yes. And those experts are not cheap. I mean, those are very well trained over many, many years with a PhD in geophysics or petroleum and so on.
Right, right. And so using sort of similar approaches here, again, deep learning models to say can we actually create models that could replicate or get closer to human level decision making?
So that's a good question, and I want to really bring something very special and different about this problem. And this problem actually is of the subsurface imaging. Is although the data available to us is mainly coming from exploration projects, but you can think about basically even CO2 capturing and geothermal and planet discovery to see what is really the subsurface of Mars, for example. It has quite a bit of really implications. But the challenge in such a geophysics problem, to me, it's very, very similar in terms of constraints to the medical and healthcare and medical imaging problem. Why? Because I experienced this myself in both of these cases. If you bring two geophysicists into the same room, and each one of them have 30 or 40 years of experience, and you give them this kind of a seismic volume, what they will tell you basically, where is the salt dome or the fault or this, almost will never agree among themselves. It's almost there is this kind of a discrepancy between, because back to what we discussed earlier about the experiences that really input into this decision-making process. So the challenge in here, in the typical machine learning of natural images, you can rely on a crowdsourcing to come with labels and annotation. You can have a crowdsource basically, and everybody in the world will know this is an airplane, this is a dog, this is a cat. So it's very easy to do that. But now to rely on, either for an X-ray or an MRI or an OCT scan or a seismic data, like, you need somebody who's really expert, not only have a degree, but also really kind of somebody who has worked with the data, which is extremely difficult. But even if you get that, to get 50 of such individuals is even more impossible. So the challenge now to the machine learning, which is a very important kind of part of machine learning field, is that how do you train a network, but not using supervised machine learning that you mentioned at the beginning of our podcast here. The idea now, how can you train without having access to, you have access to data, but not annotation, not labels. How do you do that? And this is actually, we worked heavily, and there are some other groups who worked on this for either medical or for geophysics, or from a theoretical point of view in the neural network. It's very fascinating. How do you do this kind of a weakly supervised or self-supervised kind of machine learning? And this is a very good application of it, because it's almost impossible to get ground truth annotation unless you start to really drill into the Earth subsurface, which is very expensive.
Yeah, so I wondered if there is a possibility, Ghassan, to actually remove people from it. So exposed, you would know, let's say we are, thinking about hydrocarbon exploration, and you have the structural features where you are doing a test well or something like that, and the outcomes. And so rather than relying on the expert, I wondered if you can just use the raw data and the outcome to determine if the machines can actually build up expertise.
Yes, this is fascinating, and that is actually something we did in relying on the data itself to come up with an initial annotations, and we leveraged our what we know from image processing and from modeling images, statistical models of images. So the machine learning itself, it come up with annotations, but the beautiful thing about that is because the machine is coming up with these annotations, then we have a score. We have kind of a probability or an objective score, how much we are really relying on this. For example, annotation for this first data, how much trust do we have in it? Excuse me. And the good thing is you can use that certainty into the annotations to really empower your training of the network. And we showed that actually in a couple of papers where we showed that the use of how the probability of the learning itself, as well as the probability of the annotation and the labels themselves together, make actually a better model. It's very interesting, basically, application. However, I want to be, this is something every time I go to a geophysics event, I mentioned this at the very beginning. And the way I look at this is there is geophysics, but also at the end of the day, there is geology, right? And it's really fascinating because geologists actually is much harder to get from them, to write down why they make these observation and decisions. But I look at this kind of just the same as in the medical field. I look at these machine learning kernels as tools that can work side by side with the human being, but not for the machine to only be relying on the human being at every single step, but every now and then in an active learning setup, they can really change the learning process here and there. But I look at them as an assistant tool to these experts, not to replace these experts.
So I want to finish up with another paper from the medical area. So relative afferent pupillary defect screening through transfer learning. So these are abnormalities of the eye.
Yes. So this is actually something we started work on in 2016, and what we noticed at the time from talking with ophthalmologists, it was really fascinating to see the numbers and to look at, given the aging population, just if you look at the US alone, look at the aging population and then look at how many ophthalmologists out there, even with the best prediction from the medical schools in the next 10, 20 years, there is not really enough. Every ophthalmologist have to see is 2,000 to 1 kind of ratio. And things become even much worse. We spoke with a few ophthalmologists in India, for example, and the queue basically they have in these clinics, you are talking about, it will take them few years basically to see everybody in that queue. And the problem is to schedule a visit to the doctor, to the ophthalmologist and eye doctor, it takes quite a bit of time. You go there, and then if you, like it's a 4-hour, that's what we talk to some locally hospital, it's a 3.5 to 4 hour and 15 minutes window. And the real time of the eye exam is in 10 to 15 minutes. And what we ask ourselves, two things. One, can we bring the eye exam closer to where the patient is, either is at home or maybe in a mall or maybe in the workplace or in a primary physician or the schools for children or pediatrician, for example. So the first thing, we have this component of a hardware, like some kind of an eye exam hardware. At the same time, we'd like to have in the cloud this kind of an AI tool that kind of does an initial screening. We are not saying this will do diagnosis. It will just have a recommendation, basically, to say, yes, you really need to see the doctor immediately, or it's not really high risk, but you need to see in the next few months, or there is no need to see the doctor, right? So we created this kind of a head mount display. It looks like a head-mount display, but in reality, we have sensors and cameras that they look at the eye, and they try kind of to come up with capturing with kind of an audio mechanism and some lights to guide the patient. And so they put that device on, and then there will be audio with instructions, what to do, where to look, and so on. And this was an experiment, the paper that you're referring to, just to look at basically kind of if you look, one of the most kind of popular test is when you have this light into the pupil to see how the reaction of the other pupil in the other eye.
Yeah.
And this paper just was about that, but our device is really doing more than that. And it's really fascinating how we can do this whole thing into 17 seconds capturing a video, and then it sends basically kind of this to an AI model, and then within a few seconds you have basically kind of a recommendation. And we took that to the next level, and we said, okay, now we have a device closer to the patient, but let's see now do tracking of these patients, how they recover after injections, after because after a certain surgery, the patients go home, and then maybe they are very disciplined about their medication the first week or so, but this compliance with the medication is a very big problem after surgery for the eye, and then 6 months later they have to come back and do something major. And what if they have that device? And we have also tracking, not only tracking for such a, like an outside of the eye, but also for their OCT scans, their fundus images. And we have been talking to quite a bit of ophthalmologists across the nation here, from the West Coast to Chicago to Texas. And they are all on board because they said, if you can save me 2 minutes per patient, basically that means I will increase the number of patients and see dramatically every day, because I have a kind of a classification to see who's really the one I should see first. And this way they will not have an appointment to somebody who's not supposed to be there. And that's actually, this is something we are still working on. There's quite a bit of development, and we see there is a path forward to use this machine learning and here to really come up with customized like a treatment for the patients, because you can really have this AI model that really kind of it keeps tracking and customized to this patient over years. And there's quite a bit of really objectives here to really prevent blindness at the global scale just because of AI. And I'm a true believer that this is something I see that we as humans are really capable of coming up with this, and I think the future is very bright in this domain.
Yeah, I fully agree. I mean, there are multiple benefits here, right? As you say, really the quantity of patients is going to continue to increase because everybody is getting older. There are many diseases that are progressing with age, and so not only to make the doctor more efficient in diagnosis, but also, I could imagine something like this could be a home kit that you can do more measurements on more continuous basis. And,
Sure.
It's not like, you are going to make a diagnosis, but at the very least, it puts you into that red, yellow, green bucket, type situation. And if things are progressing in the wrong direction, then you go see the doctor, something along those lines.
Absolutely, exactly. And you can really add to it another, biometric kind of measurements, and then kind of add this kind of that profile. And it's really something just you can have it in the living room, right? It's just a small device. It looks like a consumer electronic kind of device, but it really it prevents blindness eventually, and that's really our objective out of this work.
Yeah. Yeah, so in conclusion, Ghassan, you have done a lot of work in this area. Some people say there is a lot of hype in artificial intelligence. We see applications in many different directions too. So what's your sense? If you look forward 5 years, where do you think we will be? Are we making progress in real applications in these areas? I mean, we discussed some of them already. Where do you think we will be in 5 years?
So I think this is really kind of, always the question on the table when it comes to AI. And yes, I mean, there has been a hype. I think it's mostly behind us now, because there was a time or period where people thought that having an AI just increase data, and then you have a big hammer that can solve everything. You have a tool that can does anything. But I think people really, I mean, it's which is really important, and this is something I really teach in my classes, to set expectation, because it's really important to know the limits of AI and machine learning, and when they really work, when they are not. And that's why the analysis, the understanding of them is extremely crucial in that. And I believe there are kind of there are these 5 years from now, there are certain applications that are really taking shape, where we know that the AI will be extremely important to the society and the human overall. And we believe in those, like either really medical applications, other transportation applications, even education. For example, given this pandemic now, we have kind of a tool where we rely on AI to do some kind of character recognition to grade exams very quickly. Definitely, we as the professors and the instructors, we are part of the process to approve these decisions by the AI, because these are grades. But they really kind of reduce the amount of time quite a bit. So I always say AI and machine learning, we have to look at them as they assist the human. They are side by side. They will never replace the human being, but they will be assistant to the human being. And I believe that 5 years from now, we'll have a better working systems that do just that.
Yeah. Excellent. Yeah, this has been great, Ghassan. Thanks so much for spending time with me.
Thank you very much for the invitation. I really enjoyed talking with you.
Absolutely. Thank you.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.